That's it. No, that's true.
All right. So our first after lunch speaker is Chen from University of Michigan, Statistics.
Hello, everyone. My name is Chen, and today I'll be talking about some spatial-temporal data tensor completion work that we have been working over the past few years. If you're interested in checking out our work, this is a newly developed real-time focusing website that we had been working on. So let's get started. The motivating scientific problem that we had is for space weather monitoring. Typically, before you travel, the first thing that you look at is what is the weather forecast to decide on what to pack. So for space travel, that's the same issue. You cannot try to look at space weather forecasting. So space weather forecasting means that it's not only about the cold or hot days. It's really more about radio blackouts or solar radiation storms, geomagnetic storms, and those are all coming from the sun. So you can think about the sun as being a super angry object that can just throw a tantrum at any time, and that actually impacts the astronomers and the near-Earth environments. So one simple example is that during Artemis 2, they have to closely monitor the space weather events. And one of our models is actually one of the models that they got tested out during the Artemis 2 mission. I'll talk about it briefly, but the thing is that if there's a major solar radiation coming in, the astronomers needs to take extra caution before they get impacted too badly. The worst scenario coming from solar energetic particles could actually kill an astronaut if they get out of the spacecraft. And in our daily life, our satellites gets impacted, and high altitude aviation can get impacted based on space weather events. And sometimes it causes massive scale airport delays, and it causes massive power grid failures in general. So we kind of monitor the space weather events very closely in real time. So here the keywords are monitor, real time, and a large scale massive data sets. And that's the major motivation of the statistical work around the space weather forecasting. So today I only give one particular example of one data set that we have been working on, which is called the total electron content data set. So here is the sun, and then this is our near-Earth environment. There's one layer at the upper end of the sphere called the ionosphere, and this layer has a lot of electrons over there, which I'm plotting over here. And the satellite communication and the GPS positioning rely on this particular layer quite heavily. So the total electron content is one of those quantities that people actually monitor in real time around the entire globe. And this is the quantity we're interested in learning. And the importance of monitoring that is really about positioning services. Sometimes in certain days when there's a major geomagnetic storm coming in, when the sun is throwing another tantrum, then the total electron content maps demonstrate a big change. And that big change will make your positioning services to be having floating signals that the precision of the positioning can be off by tens of meters at least. So that's why we need accurate monitoring of total electron contents. In terms of real-time monitoring of total electron contents, we need to make measurements. From a statistical perspective, we're most curious about what kind of data set can we collect. So the way that we monitor the total electron content based on this particular plot is we're actually just counting how many electrons cross between a ground receiver and a flying satellite. So the keyword is ground. When you have a ground, you could draw that line and calculate this vertical projection to calculate the total electron content. But the Earth is covered less than half by ground. So we have a lot of missing data in this raw observed total electron content maps. And also, it's not evenly distributed. For example, in some wealthy countries like the United States, we have really good signal coverage because we have a lot of ground receivers. But in some other parts of the world, the data coverage is much worse. And for example, in China, the ground receivers are built pretty much in recent years. Instead of in the US, this thing has been monitored for years. And given this huge scale of missingness, our collaborators who has been working on total electron content maps came up with the idea of saying, well, there are too many missingness. We want to fill the map. So how do you do it? We do a medium filter. So they just do a 3x3 matrix and filter it through. Whenever you have one observation within that 3x3 block, you just fill it with the same value. So we have this lower resolution version, but it's still not super satisfactory because you can see the colors are indicating the strength of the total electron content values. The larger the value, the more the potential disturbances that we have. So we're actually quite interested in this central region, which is actually the sun-facing side. So in this central region, we just have too many missing data points, and they are actually not missing totally at random, or not missing completely at random, that you can just do a nearest neighbor matching. And what they want to recover is something that looks like this. So this is what they did, smoothing and trying to incorporate some physics knowledge to get to that map. But they are not super satisfied with this particular map just because this over smoothes the signal and do not preserve a lot of the important information for near polar regions, which is very, very important for space weather monitoring also. So based off this particular data set, we try to mathematically write down what are the actual problems people are trying to solve. So we can focus this as a 3-mode tensor data in terms of spatial temporal data. So this X is m times n times t. You can think about it as longitude times latitude times time horizon. So m is equal to 181, n is equal to 361, and then t is a huge number because we have this map every 5 minutes and we have 20 years of data. So this is a massive data set that we have, and it's a massive tensor. And if we just cast it as a big spatial temporal data set, we have to handle too huge of matrix inversion problems. So in terms of the missingness indicator, we can define this omega as the missingness indicator. And the 3 statistical questions that we have been working on over the past 5-6 years include video completion. How do I get the entire complete video of total electron contents? And the second one is called map prediction. We want to predict what's going to happen in the next hour, in the next day for this total electron contents, given the past history of the total electron contents and some summary statistics from the sun. Because the root cause of the change in the total electron contents is actually coming from solar activity. And we do monitor solar activities using different kinds of instruments. So there are external predictors and there are history, and we want to predict the future maps. And one important thing is that we want to do this in real time online. And another thing that we're very interested in, which is also very hard to handle, is proper uncertainty quantification for the 2 problems that we mentioned above. As you would imagine, intuitively, for those big patch missingness, the uncertainty of missing data imputation will be much bigger than for example, in the United States, when the signal coverage is so good, uncertainty interval is actually small. So how can we come up with a reasonably heterogeneous uncertainty interval for the imputed pixels for this total electron content map? So today, I'm not going to cover all of those, but I'll point you to some of the references that we have and cover some of the products that we have. So the first model that we came up with is based on matrix completion methods, because at each time snapshot, it's essentially a matrix completion problem. So if we want to frame this as a matrix completion problem, essentially is a regularized loss problem. So if we denote the partially observed matrix by X and the binary indicator for the observed entry is omega, then the projection operator P omega just maps the observed entries to itself and maps the unobserved entries to be 0. So coming from standard matrix completion literature, we just need to solve this regularized optimization problem where this is the goodness of fit L2 loss based on the observed pixels. That's a red term. And then the blue term is a regularization term, penalizing the matrix complexity. So here there's a lot of different kinds of choices that we have about choosing what kind of penalization that we have. So we chose a pretty easy one called the soft impute algorithm. Essentially, we write the matrix M, which is a true matrix, as two factors, A times B. And then the penalization here is the L2 norm of A plus the L2 norm of B. So if you think about the loss function itself, it's entirely L2 in terms of A and B. So we just do alternating least squares. It's a very simple computational algorithm, and in fact, with fast convergence. And we can result in a map that looks like this. Honestly, when I look at the RMSE from this map, I was very happy as a statistician. Because actually RMSE is so competitive as compared to what data products that they already have from the geospace literature. But they were essentially laughing at this map for like half an hour before they can give me any comments because this is totally fake to them. We are creating those artificial holes in the strong signal region. Anything that has a tiny little bit of physics knowledge will tell you this is totally wrong. But why do we still get very good RMSE? Because our evaluation criterion is still based on the observed pixels. And we're fitting pretty well on those regions. And then for the big patch missingness regions, we're regression towards the mean. And for this map, because the signal region is relatively small, regression towards the mean means that you're just imputing a lot of near zero values to those regions, which is totally wrong. But that gives us a good starting point that at least we can preserve a lot of the polar region, very refined features very well because it's data driven. On the other side, they tell us what they did, and we were able to mathematically write down their procedure also. So they are doing a kernel smoothing. It's called spherical harmonics. Essentially, it's a basis expansion based approach. So that's the map that they showed to us using their particular approach. And we were kind of laughing at it because it's so smooth. It's as if you're just not taking the data super seriously. And RMSE is so bad. How can you tell me this is good? So with that dilemma between from a purely statistical perspective and a purely physics perspective, we say, is there a middle ground that we can actually hit based on this problem such that we present this massive scale structure that satisfies the physics in the less covered regions, but also respect the data a lot more to capture the refined structures near the polar regions. So the method that we came up with is called Vista. We try to simultaneously impute all of the time frames instead of one frame at a time, trying to borrow some information from both temporal side and the spatial side. And in general, the loss function that we finally have is from time 1 to all the way to time t, we still have an L2 loss for matrix factorization based on matrix imputation. But then our loss function, the penalization term includes 3 different terms. One is the vanilla soft impute penalization. Because this is a matrix factorization-based approach, this summation of the L2 norms will give us sparsity constraints so that we have some kind of lower rank property over there. And then we can count on this temporal smoothness penalization to help us borrow information from neighboring time points and actually extended neighbor time points. From a Bayesian perspective, you essentially get a shrinkage estimate or weighted average as the final estimate. And we also want to have some auxiliary data penalization where YT is a full smooth map that they actually provide based on the physics model fitting. It's a very simple algorithm, and we were able to test it out using a bunch of simulation studies where we randomly masked out big temporally moving patches from the from a globally smooth data set. And it seems like our proposed algorithm can get the best margin out of all of the competing algorithms that we compared against. I'm not going to go into details for this because just like any other talk, people will just say our method is the best. So that's the take-home message for that. But when we actually apply it to the real data set, we kind of encounter the difficulty of the tuning of the model for storm day versus non-storm days. So during the storm days, when you have a geomagnetic storm, again, when the sun throws another tantrum, the change of the time series is very, very fast. Or in other words, it's not really a stationary time series that we love anymore. And so the hyperparameters, especially the regularization terms for the temporal lag terms, will have to be quite different from the non-storm days where we have a lot of stationarity. So we kind of did different kinds of tuning procedures for the storm day and non-storm day separately. And we were able to show for majority of the frames that we look at, for majority of the time slots that we have, we can improve on top of all of the existing approaches in terms of this imputation algorithm. So as a summary, in this particular first thing that I talk about, the VISTA algorithm, we were able to use temporal information, spatial continuity, and real data to actually give a fully imputed total electron content map over the past 15 to 20 years. And we actually wrote up a data product paper for people who are interested in studying large-scale tensor data or spatial temporal data to use. And it's actually used by the space weather community quite a lot nowadays to initialize their numerical simulation model, and also as a benchmark that they compare the numerical simulation models against. So this is our website for the VISTA TC dataset. Right now it's stored at the University of Michigan library system. It is a very old system, so everything is zipped up in month by month. So downloading wise is not the most convenient, but that's the best that we can do with the library system. And we spend a lot of time with the outlier removal and validation of the dataset. Because commonly you ask the question for this reconstructed total electron content dataset is that how can you tell your imputation is better than others when you have completely missing data in the big spatial patches? So actually we have a different satellite that takes measurements of a different quantity, but a derivative of that particular Earth circling satellite is the total electron content. But that data is extremely sparse, so that we never use it for total electron content purposes. And that's called a LEO satellite. Some of you might have heard about. So we actually derived the total electron content values from the LEO satellite for the very sparse observed entries from the big patch missingness regions. And we were able to validate our imputation with the LEO satellite observations very well. And I guess that is the reason why we were able to get this paper published in Nature Scientific Data. And this is a screenshot of our VISTA TC database. This is a raw observation. This is the median filtered observation. And this is our final data products. All of those entries will be available if you download our data set. So just in summary, actually right now it's already a couple of years later. So we have more than 16 years of spatial temporal data set with 5-minute temporal cadence. So each month you will have more than 2,000 matrices of size 181 times 360. It's a pretty large data set. And it's open source. Anyone can use it for validation purposes. So based on the previous algorithm is we have to do the VISTA algorithm month by month because it's an iterative list of squares and it's based on matrix completion algorithm. So it's not like extremely fast and it's not super scalable, especially along the temporal dimension. So if you think about when we have 15 years of data and we want to do it all together, there will be a lot of computation, a lot of iterations, and the number of AT, BT factors that we have will be equal to big T, which is the number of time slots that we have. So in order to speed it up, we try to incorporate some knowledge from tensor representation and propose this new computational algorithm called FLOST. I'm really happy that our keynote speaker earlier today laid out all of the foundations about the Fourier domain and Fourier transformation so that I can skip all of those discussions. So essentially, the key idea is that we want to restate the total electron content completion problem as a tensor completion problem. Again, it's the same thing that we had before, but just with a little bit of extra notations. The T is our big tensor. And the missingness is still indexed by omega, but here we're assuming for simplicity that the missingness is IID Bernoulli P. We are actively working on extensions to make it a non-IID Bernoulli P, but just bear with me at the moment because that was the best that we can do from theoretical perspective at that point. So the framework is trying to tackle the unique challenges of both the stable TEC for many regions and some rapid fluctuations for certain different regions, the heterogeneous fluctuation type across different regions. So this thing is called a Fourier low rank and sparse tensor framework. Essentially, we just treat this entire tensor as multiple fibers of time series. If you look at one particular geographical location, it's a very, very long time series, and we can call it a particular fiber. And for this, each of those time series, if you transform it to the frequency domain, we can actually think that majority of the information can be captured in the first few elements in the frequency domain, because high frequency information does not exist for many pixels. And for scattered pixels, there will be some high frequency information, and those will capture the heterogeneity. So that means we have this hybrid thing at the Fourier domain that's illustrated in this particular figure. So in the frequency domain, for the first few slices, for the first few frontal slices, we have a low rank structure. And we can still do low rank based regularization. But for what's left in the frequency domain, at the very high frequency domain parts, is just the L1 regularization of our entire sparse structure. And this fits well, very nicely to the spatial-temporal data framework, just because total electron content most likely will not change unless there's a solar storm coming in. And when there's a solar storm coming in, it's really scattered and only impacting limited number of pixels on the total electron content map. And because of this formulation, we're actually able to derive a parallelizable computational algorithm to solve the total electron content imputation problem in a scalable fashion. So this is the model. Essentially, it's just a signal plus noise, and it's Gaussian noise, nothing fancy over there. And the loss function is still L2 loss for the matrices, and then this is the sparsity loss plus the low rank loss over there. That's the sparsity penalization and low rank penalization. But one important thing that I want to point out is that in our previous matrix factorization framework, typically the loss function is P omega of T minus Y. But here we're actually separating out the true tensor and making the P inverse to be with the observed tensor. So the innovation here is that by writing the loss function in this other alternative fashion, our computation will become parallelizable, so that it solves the computational efficiency problem very effectively. So in the frequency domain, essentially we're solving k+1 independent problems with K of the problems being the low-rank matrix factorization framework, and the rest of the problem just the sparsity imputation framework. And we were able to derive some theory. It's mostly useless in practice, but there's just the only use that we actually want to have of this theorem is the guidance of choosing the hyperparameters and also like telling us what are the scenarios, what dimension of the matrix and ranks that our method will probably succeed. So we, numerically, we compared this with the state-of-art video and tensor completion algorithms, including ablation study where you only have low-rank matrix factorization across all frequency domain instead of having a combination of those. And in terms of computational time, we definitely dominate in terms of as compared to all of the other algorithms. In terms of accuracy, we're just a comparable. So we're not the top, we're also not the worst. But those existing literature always get very similar accuracy anyways, but computation-wise, we save a lot. And this is actually based on our implementation without parallel computing. We're just doing a for loop for that parallelizable part. So actually in practice, this can be even faster. So here I just want to quickly conclude that we had this algorithm called Vista that enabled us to construct this total electron content database. Is kind of naive from the construction perspective, but the performance is actually so far the best. Regardless how hard we try based on more fancier tensor completion algorithms, we actually haven't really beat the Vista algorithm yet. So the database that we send to the space weather community are all based on this Vista algorithm. But from our tensor completion algorithm perspective, we were actually able to derive the heterogeneous version of the uncertainty quantification based on two different approaches. One is based on conformal prediction, and the other is based on asymptotic nomadic derivation of low tuple rank tensor completion. And we also have some video prediction papers recently written. And one more thing is I want you to check out our newly developed space weather prediction interactive lab and check out our real-time focusing models.
Okay, thanks so much.